One second, I screwed something up. Let me stop recording over here. Yep. Perfect. I press the space bar, which apparently starts and stops recording. I did not expect that to happen, but hello, wonderful people of the internet. Welcome back to another episode of Simuleo. So today is going to be a relatively short stream, but I did want to get one on the books out. I wanted to do something. Hi, Minecraft modpacks have moved to a separate launcher, but I'm still using Twitch desktop app out of inertia. Anyway, I did a big refactor of my Ktain script last night that I'm really happy with. Really decoupled the code, I think. Oh yeah, super cool. You used to be able to launch Minecraft modpacks from Twitch desktop, but you can't anymore. Yeah, so I've never actually used Twitch desktop. Real Sadie, hey, how are you? Okay, so I took like a week off where I tried to figure out what the plan was with Twitch moving forward. I kind of noted a lot of the discussions and stuff that we had on Twitch, or rather on Discord. I talked about why I was thinking about moving away from stream and all this kind of stuff. The truth was, I could not find the time with my previous job, or with my current job, to do streaming regularly to the scale at which Twitch demands, and there were a whole bunch of other issues. However, starting next year, January 15th-ish, I'm actually starting a new job, which should help me out with that. I can't talk about the details of the new job yet, but I'm hoping it turns out okay. So we'll see how it goes. It's a 6-month contract to start with, but you know, they have renewal for at least a year. And it should be pretty good. I'm pretty excited for it. Hey, C252 Trash Talk, how are you guys doing? I hope you're having a great day. So today, we're going to hop into something that I've been wanting to hop into for a super long time. And anyone who's been on this stream before, pretty much ever, has probably heard me talk about this before. The Schonhage Strassen algorithm. Let's talk about it. I know I'm mispronouncing it. I don't really care anymore. Right. So I've been wanting to do this series recently where we delve into topics that are incredibly straightforward. Everyone knows multiplication, and we move to the boundary to which these things are no longer simple anymore. And that's kind of the idea behind the Schonhage-Strassen algorithm. The reason why I'm so interested in it, because this is multiplication, but with FFTs, and it's really cool. So again, today's going to be a short stream. I'm just going to get it on the book, say that I kind of want to talk about this a bit more in the upcoming week. I'm really hoping to get a video out for this algorithm by the end of the year. Like it's so weird, guys. Like as of last week, like my whole mentality just kind of completely flipped. My whole like mentality completely flipped towards the stream and how it fits into the greater ecosystem and everything else. Like last Monday, I was like, I just don't know how to make this work. And now I'm like, nah, like the stream is like the best part. Even if people don't necessarily watch it too much, that's okay. It's my favorite part. I enjoy it. It lifts up my spirits. It's good to do. Even if it's only for, you know, a small subset of the people who watch the YouTube channel, it's still definitely worth it. Pretty good. How about you guys? I'm chill, still speedrunning Your Bachelor. Good luck with that one. I don't know how I'm so late. Just got the notification. We literally just started, so you are not late at all. We're just doing a short stream today. Let's see, what do we have here? Not really, just not failing any classes. Oh, okay. Well, I mean, I figure a speed run, right? A speed run through a university degree probably entails a few failed classes, I would imagine, right? Just in my first semester. Yeah, guys, so what else was I going to say here? It's been a week since my last stream, but it felt like a long time. There were a few things I did do over the past week. For example, if I go to, let me just go to, bookmarks maybe, and then writing prompt challenge. I have actually been keeping up with writing. So I am on a 14-day streak, for writing something new every day. Which is pretty good. I don't know how long today's stream is going to be. I just kind of wanted to catch everyone up. So if you guys are interested, here's the writing I've done this past week. It's in the last 14 days. Again, not everyone cares about the writing. I just wanted to put that down there. So I think we're ready to go ahead and jump into the Schonhage-Strassen algorithm and yeah, talk about what it is and why it's interesting and maybe what we can do today in about an hour or so. The reason I'm so limited for time today is because actually there's a friend who's visiting, but my roommate and that friend recently just left to go for a walk. So I figure, hey, if they're going to go for a walk for a bit, let's go ahead and do a quick stream while they're walking. They said it would be an hour or two, so we have an hour or two for a stream. And we'll just see how long it takes for them to get back. I should be able to hear them upstairs when they come in. So whenever they come in, I'm going to stop streaming because Again, I hadn't seen this friend in like a year. They came from OIST. So it's kind of weird. This apartment is actually myself from OIST, my roommate, who also went to OIST. And, you know, right across the street, there's an oyster shop. It's kind of an interesting spot. Let's see. I was right. You're studying math. Let's see. Real Sadie, thank you so much for the subscription. Let me go ahead and put 6 Simul cows in the chat. Simul cow, I need 6 of them. So there's 1. Now just 6 more. 1, 2, 3, 4, 5, 6. There you go. Thank you so much for the subscription. I appreciate all the support everyone gives the channel. But yeah, I hope you guys are all having a great day. I don't know why this week felt like a lot longer than like a lot happened this week. My girlfriend got her PhD. I ended up quitting my MIT job. I don't know. I got a new job. A lot of stuff happened. So it's been a week. And we'll talk about it as it keeps going. Okay, so okay, let's try to figure this guy out. So I've read through this whole thing, and I'm going to be honest, the Wikipedia article here does some justice to explaining how this algorithm works and why it works that way. But I think to some extent, the only way we're going to fully understand this thing is by implementing it in code. So that's kind of what we'll talk about today. They have this diagram here explaining what it is, and quite frankly, I don't think this diagram is particularly useful. But let's just start at the start here. What is the Schonhage-Strassen algorithm? Okay, let's say you're multiplying 2 numbers, like 2 and 2. Okay, fine. Obviously, everyone knows that's 4, right? Let's say you're multiplying 2 10-digit, or 2, like, I don't know, bigger numbers, 12 and 14. Okay, that's fine. You also know how to multiply that. The Schonhage-Strassen algorithm is an algorithm intended to deal with multiplication of numbers that are like 40 or 50 digits. Large, right? And so once you start to get to these huge integers that are impossible to multiply by hand, the question is, how exactly do you do this multiplication? And the Schonhage-Strassen algorithm is the way it's done in some cases. Not all cases, but some cases. And this is the most interesting one for me because it actually uses an FFT. So I'm going to describe what this is saying here. And then I'm going to describe kind of how I want to go about explaining how this works and everything. This week, my girlfriend got her PhD. Sounds so cool. I didn't know it was 4. Fair enough. Quitting my job at MIT also sounds cool. I'm very dumb. It's okay. I realized while I was preparing for this particular script, this particular algorithm, I had completely... Do you see? Like, okay, let me just scroll down a little bit. Multiplication of 1, 2, 3 times 4, 5, 6. I apparently do not remember how to do multiplication in this way. I actually am somewhat convinced that I never learned how to do multiplication this way, because I realized throughout all of school, I actually never did this like top-down multiplication scheme. So it's really, I think I always just did approximations. So I think like I would have multiplied 456 by 120 and then added 3 times 456, you know? So I might actually learn how to do multiplication today. That might be part of today's stream because I've completely forgotten. But now I do know that this is just a cyclic this is just a convolution, so I don't have to do multiplication. Remember, this algorithm is all about minimizing cache misses. I think in some sense, yeah. Wait, does this algorithm only work over Z337? So that's my other question. I'm not really sure. Spoken like a true physicist. Yeah, I'm in a bit of a bind in that I don't remember how to multiply, but that's okay. We'll figure it out. Okay, so what is this diagram saying? It's saying we're multiplying 2 numbers, 1, 2, 3, 4, and 5, 6, 7, 8. And it's explaining how we're going to do that. So the first thing we do is we split up the numbers and we 0 pad them. So 1, 2, 3, 4 becomes 4, 3, 2, 1, and then a bunch of zeros. And then we have 5, 6, 7, 8 becomes 8, 7, 6, 5, 0, 0, 0, 0. So in some sense, this makes a lot of sense because when you do a convolution, you end up getting a signal out that is twice the length of the 2 signals you put in. Well, not twice the length. The output signal will be the length of signal 1 plus signal 2. That's going to be the output length. So we know signal 1 plus signal 2 is going to be 8 in this case because it's a 4-digit number and a 4-digit number put together. Okay, so now we have the FFT. In which case they basically just go into Fourier space, they perform the FFT, and then they go back with a recursive pointwise multiplication. So they basically FFT forward, multiply, and FFT back. That is a convolution, a cyclic convolution. After that's done, they then basically do a recombination step, which is basically just carrying. So the idea here is like, for example, if you have, let's see, this convolutional setup here, so you end up with 4, 13, 28, 27, and 18. You're going to have 8 as this digit, and then you bring 1 over here, so you'll have 8 for that digit. You bring 2 over here. You'll have 8 for this digit. You'll bring 2 over there. You'll have 5 for that digit. You'll bring 1 over there, and you'll have 5 for that digit. So that's kind of how it is. It's kind of an interesting algorithm. Like, what's the complexity of normal multiplication? What is the complexity of normal multiplication? I don't know. I suppose that's the Toom-Cook algorithm, right? Is that the one that people normally use? Toom-Cook algorithm. I think this is what they use for normal multiplication. It's sometimes known as Toom-3, named after Andrea Toom, who introduced the new algorithm with its low complexity, and Stephen Cook, maybe Cook, probably not Cook, right? Who cleaned the description of it, is a multiplication algorithm. So this one has a complexity of, okay, the theta complexity of n times 2 to the square root of 2 log n. What? There are better ways to do it than n squared. Harvey Hoven has a log n log. Yeah, that's fair. So when would this be used exactly? So this particular, the Schonhage-Strassen method, where you do a convolution in order to do the multiplication, is particularly useful when you have a huge number of digits. The high school approach. See, I don't know the high school approach. Okay, so here's the thing, guys. Do we want to... I can probably implement the Schonhage-Strassen algorithm in like an hour. I'm pretty sure I understand it enough that we could do that. In fact, let's do that. Let's just implement the algorithm today. That's what we're going to do. It's not going to be too complicated. We're just going to do it. And then after that, we can talk about where we want to go from there. Like, for example, maybe I need to learn high school math because I have completely forgotten how to do multiplication, apparently. I'm convinced I was never taught to do multiplication. Like, I think I just made it up. There were a lot of things in school that I just kind of made up. You know, like long division. I just kind of guessed at, and it always worked out, so I never really tried. You know? And there's all these other like different methods that people would teach me in school, and I wouldn't understand it, so I just pretended I understood it, and it worked fine. So I don't know. I have the fear and the feeling that I'm gonna have to learn how high schoolers or like maybe elementary school students learn multiplication. That might be something I need to do. Hello people of the Simuleos, welcome back to another episode of the Basic Arithmetics. Hey TS Jost, how are you? Okay, so we're gonna go ahead and CD into projects, Simuleos, ls here, make directory, and we're just gonna call it Schonhage. Strassen. There we go, CD into Schonhage, ls here, and we're gonna go over here, CD projects, Simuleos, Schonhage, Strassen, ls here, and I'm just gonna go open up, we'll call it Schonhage, Strassen, well, dash, .jl. Okay, first thing we're gonna do is using FFTW, and in typical, I guess, Simuleos fashion, I'm gonna open up a new terminal in here, and I'm just gonna put a giant thing here and just say, Wiglet, learning to multiply. So if anyone comes in, that's kind of ugly, isn't it? Anyway, it's fine. If anyone comes in, they know this is what we're doing, so I'm not going to worry about it too much. Okay, perfect. Let me go ahead and catch up on chat, and we're just going to do it step by step as was described in the algorithm there. This is how I learned it. Long multiplication. Thanks, Racel Tomato. Wait, what do we have here? Over here, paste. It's funny to think you need to learn high school math, like asking the Hulk to open a jar of mayo. This is how I learned it. If it's done in the ALU, then you could say that. Wait, what? School approach. Multiply each digit of the first number with each digit of the second number. Oh, okay. Shift each partial result by the sum of the digit positions and then add the numbers together. It took me well into my 20s to realize that perform the same operation on both sides of the equals in algebra actually means... Oh, right. What's it, JL? It's for Julia. I have to go pick up an order. Be back soon. See you, Rail Sadie. Because it doesn't just mean perform the same operation on both sides of the equal. Kind correct. Yeah. Right, because you can do some balancing on one side. I see what you're saying. Basically, the school multiplication is exactly the same as a naive convolution. Ah, okay. In that case, we're fine. Oh, man, like, this is one of those things. I wish I had better education. Like, I'm not knocking the education I had, but I am saying that the education I had was kind of in rural Alabama, and I'm not gonna lie, it wasn't particularly good. Like, I was valedictorian of my class, and that's saying something. Like, I shouldn't say that in case, well, there's no way anyone from high school is watching. But, okay, my point is, I don't think I learned what I should have learned in high school. You can't just add times 5 or something to both ends. You need to wrap everything in parentheses before adding it, or add everything to each term. Right. Hey, Marco Dev, how are you? Okay, so again, guys, today will be a short stream. It's not going to be so long. I'm just kind of waiting for my friends to come back. And when they come back, I'll go ahead and close stream. So it might be an hour. I don't know. Who knows? We'll just keep going. I didn't really even go to high school. Wait. Oh yeah, I think you told me about that. And obviously, whatever you can do to speed up convolutions, you can use to speed up multiplication. Right. So that's the thing. Like, this idea that multiplication is just a convolution kind of blew my mind when I heard about that. I had no idea. So Dr. Schleim's Joss. Ooh, the Journal of Open Source Software. I'm keen on that. Julia. Okay, so we're just gonna kind of knock this out. So, actually, you know what I'm gonna do? I'm gonna grab this guy, and we're just gonna view the image. I'm gonna save the image, actually. Save image as... Oh, where am I? What am I doing with my life? Give me a second. I'm lost. I need to go to Projects, Simuleos. Anytime I see a UI, I get incredibly confused. Where am I going? Oh, Schonhage Strassen. Right, of course. And then we're going to say algorithm picture. Sure. The PNG. Wonderful. Okay. And that's the image that we'll have in the upper left-hand corner. So it's a bit... Because I'm going to have to keep looking at the picture anyway. I don't know why I just closed that. CD Projekt, Simuleos, Schonhage Strassen, LS, Mirage, alg picture.png. It's got, okay, well, we're going to open up in GIMP. Right, perfect. Great, let's just, oops, sorry. I'm going to open up a file system. So it has like a weird border on the background. So let's see, what am I doing with my life again? I want to go to projects. Oh, I know what I want to do. I want to go to Quiltify. There we go. Perfect. And I want to put hsv.png behind it. Okay, great. And then the algorithm will be... Ah, that's wonderful. That is beautiful. Okay, we're going to keep that. File, overwrite algpicture.png. All right, there we go. And then if I open this up, wonderful. All right. So if anyone thought we didn't have enough color on screen, there you go. There's your color. Wonderful. Numbers using FFT is pretty good. So for reasonably sized numbers using FFT is pretty good. As far as I know, the better algorithms need ridiculously huge numbers to beat FFT. Yeah, that's true as well. Isn't Firefox one big UI? Yeah, it is. But you kind of get used to it. It has a chessboard on it. Yeah, we could play chess. I mean, why not? Okay, so recently, one of my YouTube friends, their name is 12Tone, has been playing Go. And I have considered sending him a message and asking if we could, like, both stream playing Go at the same time, because I'm a big fan of Go. Okay, so if using FFTW, we're going to write here. Here's the algorithm itself. So the first thing we have to do is split and zero pad. Oh, how am I so stupid? Don't answer that. Perfect. Okay. So the first thing we're going to do is split and zero pad. I'm just going to create a function. Okay, so my question is, when they say split and zero pad, what is happening here? Why is everything reversed? Why does it go 1, 2, 3, 4 to 4, 3, 2, 1 in this image up here? That's my first question I have. I don't know for sure. So what I'm going to do is just create split and zero pad. Don't at me. Split and zero pad, and we're just going to grab any number, which we're going to say is A, end here. And so then we want to return an array. Yes, we want to return an array. So this is actually going to be a number. and we want to return an array of values. So how do we do this? So let's just check. So a is going to be equal to 1, 2, 3, 4. All right. How do we know how many digits a has? So that's easy. It's going to be a divided by the log 10 of a will give us that. Right? Or am I dumb? I might be dumb. Let's see. It's 5x5, 64 chessboards on it. That's going to cost at least 20 bucks. No, 4,096. Okay. How do we know how many digits? Digits? Oh, is that a thing? Oh, okay. Sure. Perfect. Okay. So how would we zero pad that? So dig is going to be equal to dig is going to equal digs is going to be equal to, oh no, digits of a. All right, perfect. So 1, 2, 3, 4 has the 4 element array for. Oh, it's already reversed. Oh, okay. Then why don't we just say it's going to be equal to, so this is literally just going to be digits of a concatenated with, 1 second, I need to think about this. Thinking takes time. Zeros of int. I need to think. And then length of digits of a. And then we're going to want to vcat that. I think that'll do. Oop, did I miss something? Probably. Perfect. Wonderful. That's exactly what we want. Great. So what I'm going to do is I'm actually going to say digs for digits and just deal with the notation here. Don't be mad. Don't be mad. Get glad. Is going to be equal to digits of a. Sure. And then in here we're just going to say return vcat of digs with zeros of int and then length of digs. Something like that should do. Perfect. That's it. Split and zero pad. Right quick. Go over here. Include. Not x.jl. I want to include Schonhage Strassen.jl. And then we have split and zero pad. So if I do split and zero pad 1, 2, 3, 4, I should get 4, 3, 2, 1. 4, 3, 2, 1, and then 0, 0, 0, 0. Okay, this is kind of what we want, but not quite. Let me go ahead and catch up on chat. Something to watch out, though, is that when you use floating point FFT, you'll get some rounding errors. Right. The way to do that in Python is to convert to string. Yet my bad, numbers are hard. So that's correct. The FFT does not naturally work over integers. Am I dumb? FFTW package might not work on integers. So we might have to think about how to do the rounding errors. But what I think I'm actually going to do here is I'm going to read in two vectors, A and B, and we're going to say digs A, digits, A digits, and then B digits. And this is going to be digits of B. And then we're going to say return the vertical concatenation. So we want to return two different ones. So let's say that this is going to be equal to, and then we're going to return A digits and B digits, A, something like that. By the way, guys, if like the music or something is weird, just let me know. So A digits is going to be equal to vcat of A digits. And then we want length of, what do I want here? Length of, give me a second, I have to think about this. I'm not very good at this. B digits. There we go. And then add that, and I think that'll do. And then we want B digits is going to be equal to the vertical concatenation of B digits. And then length of A digits. A digits, great. So if we do this and we include this, and then I run split and zero pad 1, 2, 3, 4 with 5, 6, 7, 8, we should get two groups of zeros, sorry, of int. Put that down here as well. And perfect. Try that again. There we go. So now we have our two. Okay, I'm dumb. Yep, I'm dumb. 1 second, let me. How about we don't? How about we just return? All right, you guys are gonna. Let's just return this, comma. This. And now we're just gonna $sign in there and just pretend I can code. Ah, no. What's this going to? So this is fine. This is fine. Ah, that's not fine. Now let's try that. Perfect. Now we have our split and zero pad done. Okay. I don't think FFTW does integers. I think you're right as well. The way to do that in Python is to convert to string. Good old. So I don't think the algorithm works over integers either. I think the algorithm maybe. Okay, that's a good point. I'm actually not sure how this works. So let's do an FFT. So the issue is that this FFT is actually not a real FFT. It's what's known as a number theoretic transform, which is still an FFT. But it is an FFT over integer space. And because of that, it is a bit weird. So maybe what I'll do is I'm just going to implement all the other bits of this, you know, like the carrying operation next. And then we're going to come back and try to figure out how to do the FFT and all that kind of stuff. Well, okay, let's sketch everything out, and then we're going to figure out where it breaks. Let me take a look at this DOI. Actually, I've never... How do you look up DOIs? DOIs? Integer fast Fourier transform? Right. This was published in... what year? 2002, right. Although it's surprising it's in 2002. The Cooley-Tukey method came out in 1970-something. According to Wikipedia, it only works for rings of order 2n+1. That is correct. The length of a digits hasn't changed. Has changed. Yes, it has. I fixed that. Sorry about that. I'm dumb. Though I don't know if using integer FFT, you'll still end up with fixed point rounding issues. Sorry, I gave DUI because figured Nightbot might object to HTTP links. I actually don't have Nightbot. So you're happy to post whatever spam you want into the channel. Probably shouldn't have said that. Anyway, so let's just keep going. So the next thing I'm going to implement is the carrying operation. So we're going to do function carry. Function carry. And this is going to take in a vector, which we're going to call v. Something like this. And here, so let's see. Okay. It has a vector of numbers where, so we're going to say 4. Oh, I really got to think about this. No, this will be fine. So 4I is equal to length. 1 second. Length v minus 1 all the way down to 1. End here. So we're going to go through the array, and all we're going to do is we're going to I think I need a function to turn a vector into a number. So let me go ahead and create, or is it we're 85 and 3. I was really hoping no one would ask me that question because I have no idea. Actually, C252 seems to know where the 337 comes from, and I'd love to hear, because when he read, does this only work in 337 space? I was like, yeah, but I don't exactly know why. There is a mod 337 here, so I don't know is the short answer. We need to figure that out. It's part of the mystery of the algorithm. Because apparently it only works in 2n+1. Right, but n is the length of the array. So n is, no wait, what is n? N is rings with 2n+1 elements, where n is going to be the length. Yeah, it's the number of digits in the array. So 337, what's 2 raised to the n? 337. Wait, no, there is no 2 raised to the n that would give you 337. Correct. Now I understand. Is not 1 greater than any power of 2? So wait, what is a... Give me something. Let me see if I... Mersenne prime. What are these guys? These are like 1 minus a... what what is this again? It's 2n minus 1, right? Not 2n. So this is like the opposite of a Mercian prime. That doesn't help me in any way. I just thought I'd mention that in case anybody wants a little bit of trivia. Okay. Again, let's go ahead and implement the carrying operation. We're not going to worry about it too much. So we're going to slowly but surely work our way through the method. Good. Okay. So, the carrying operation. We're going to go through the vector. Bit by bit. Oh, wait a minute. Am I going the wrong direction? Okay, see, the recombination step here. Wait a minute, what? Okay, so you bring 4. Okay, so 7 is the first digit. 7 is the first digit, so that's the biggest digit. So, okay, so I am going the wrong direction in the set of digits then. So we actually want to go the normal direction. So this is going to be length v. And this is just going to be 1 to that. I'm sorry, guys, I'm dumb. So we're going to go through that. Let me scroll back down a little bit. Okay, a little bit more. Oh, I'm a bit lost. That's okay. What about 85? It says it's in the eighth root of. It says it's the eighth root of unity. Yeah, so roots of unity are useful for the number theoretic transform, which again is an FFT along a essentially a clock. So it's an FFT along a an integer clock. Now I'm going to try to refactor my edgework object so that it can be partially initialized. So A, I don't need to ask the user pointless questions, and B, I can more easily patch it for tests. Cool. Yeah, it sounds good. I wonder if there is a pattern for this. Oh, a pattern for like the programming structure that people will be using? I don't know. But it's an interesting question. So, okay. I feel like there must be a way. Is there already a carrying operation in Julia? I know this sounds dumb, but carry. There must be, right? Carrying operation Julia. I don't want to like how to think like a... No, okay, it doesn't seem to exist just off of... PSA, floating point arithmetic, off topic, Julia Lang. Thanks, Julia. How to think like a computer scientist. Julia, OpenMP. Julia, image, set image using OpenMP. Wife carrying number 9, Julia Galvin. Wife carrying, Julia Galvin. I don't care about carrying your wife. Okay, whatever. Although I clicked on it. That is something. Try to look at source code for a big integer Julia library. I'm sure it would be there, right? I wonder if there is a pattern for this. Maybe some factory pattern, but I'm not sure. Okay. Let's just implement something dumb and just put a to-do statement in here saying, hey, look, there's probably a better way to do this. So to do, there is probably a better way to do this. Check. Big integer. Source code. Integer source code. Okay, do you guys ever just forget how to read? Yeah, that happened to me. I've forgotten how to multiply. I've forgotten how to read. I mean, at some point, I'm just gonna like devolve into like a toddler, you know, babbling about, you know. Okay. So since we're already saying that we're gonna do this a dumb way, okay, let's think here. What I want to do is I'm gonna go through each element, and I'm then going to add anything above 10 to the element next to it. So for example, this is going to be length of v minus 1. And we're going to say v of I plus 1 is going to be plus equals v of I think, can I just do, how do I get the tens digit? Like, how do I remove, how do I find everything but, Oh, I'm lost. Anonymous cheer, 101 bits. Thank you so much for the bits. I really appreciate it. I hope you're having a great day, whoever you might be. Okay, so I'm gonna ask something. Subtract 10. If you, okay, let me just open up a new. Why can't it be larger than 19? I think it can be larger than 19. I mean, they have an example right here of it being larger than 19. Here's like 32, 52, 61, so on and so forth. So I think it's clear that it can be. So let's say we have 28 or something. So I want to make it so we keep 8 in 1 and we take the 2 and bring it out. I'm sorry that I'm stupid. Like, I do apologize. I know I'm an idiot. Let's just try to figure it out. Hey, Amaris, how are you? Okay, so we want to take the 2, move it down to the next digit. So the question is, how many times do we have to divide by 10? To get to... How many times do we have to divide by 10? I feel like that's what the... You won't ever end up with 28, though? Yeah, so what I want is a 2 and an 8. That's what I'm looking for. So I think if I do log... I'm going to do something stupid, and you guys are going to hate me for it, and that's okay. You know? Some people are not worth forgiveness, and I'm one of those people when it comes to programming. So I'm going to do log base 10 of 28. And this should give me 38. Not what I thought. Today's stream is giving me a lot of anxiety. This is how I feel when presented with a simple problem to solve on a whiteboard in an interview. Right. So maximum it could be is 9 plus 9, which is 18. Wait, why can... You won't ever end up with 28, though. Wait, no, I don't understand why we can't end up with 28. They clearly end up with 28 here. Or something higher than 10 here. Right, so here's 32, 52, 61, 60, 34. So, I think you can end up with something larger than 18. I think it's because of the way that they did the convolution and everything. It's not 1 digit per cell of the array. Well, no, it's 1 integer per cell of the array, right? And so... I mean, okay, we can... the question is, how many times do we have to divide by 10, right? Well, no. The question is... So the question is... Why am I so dumb? Okay, so the question is, how do we... We know it's 2. I can just look at it. I can look at the digits. So what I can do is I can look at the digits. Working in base 10 is... perverse. I'm sorry, man. But I can look at the digits and I can concatenate all digits above. Okay. I don't, in principle, I imagine these could be over 100, right? So let's just take that case into account and let me do digits of 128. Okay, this is going to give us 8, 2, and 1. And what we want to do is... what we want to do... I'm going to have to do this anyway, so let's just go ahead and create our function. X mod 100 divided by 10. 28 mod 100 is going to give you 28 divided by 10. Gives you 2.8, and you want 2, so you want to floor that. I learned how to do it for polynomials, but integers are quite annoying to work with. Even the same. Okay, so here's what I'm going to do, guys. We're going to create a function to solve all of our problems. Function, and this is going to be vector to int is what I'm going to call it. It's going to take in some sort of vector v, and it's just going to return some, let's say, what should I call it? V-sum, vertical sum, vertical concatenation, carried sum, I don't know. And here, I'm just going to call it sum, and you guys are going to have to deal with it. Okay, so we're going to say for I is equal to 1 to length of v, and here, oh, I just have too many end statements. Okay, so here we're going to say sum plus equals 10 raised to the I minus 1. That is 1 minus 1. Let's do I minus 1 times v of I. So this will mean that we add 1 times v of 1, 2 times v. Okay, so let's just see what this does. And then in the end, we want to return sum. Okay, let's see what this does. So we're going to include. It might break. No, it works. So we have carry vector to int. So we're going to do vector to int, and we're going to read in the vector that is 1, 2, 3, 4. And this should return back the... Okay, it returns back 4, 3, 2, 1. Is that the correct order that we would expect? I'm not really sure. 4, 3, 2, 1. What we might actually want to do is go the opposite way. Yeah, maybe we want to go the opposite way through it so that it... Okay, so if we do digits, let's do 1, 2, 3, 4, right? This is going to give us 4, 3, 2, 1. So in principle, if I do vector to int of digits of 1, 2, 3, 4, I should get back digits of 1, 2, 3, 4. I should get back. Yeah, okay, good. Works just fine. Perfect. I learned how to do it for polynomials. I bet all the modular operations are going to take longer to compute than the rest of it. Maybe. Okay, so this is dumb, but it'll work. So now what we're going to say is going to be v of I, digits of v of I, so this is going to be 2 and 8. And I want to just grab 2 to end. And we're going to do vector to int. Ooh, look at that. That looks like it might do something. And then in the end here, we're just going to return v. And I think what I'm going to have to do is do carry exclamation mark. All right, let's see what happens. Include, and let's do carry. And we're just going to read in, let's just read in a vector that's going to be 18 and then 2. Okay. Right? Okay, it returns 18 and 3. That's because I forgot to set the other array here. So here we're going to say v of I is going to be equal to... my notation sucks. I'm sorry. You guys are just going to have to deal with my crappy notation here. Digits of v of I. And so this is going to be digs from 2 to end. And this is going to be equal to digs of 1. Okay, let's try this again. Include, carry. Okay, we get 18 and 3. I think that is correct because we... No, we get 8 and 3, right? Because you have 18 in the 1 spot and 2 in the 10 spot, so this is correct. Good. Okay, we're getting there. So now the trick. Now what we want to do is put in this vector that they give us here to make sure it actually gives us back the output vector. Would it be easier with the binary system? Let's see. Usually you do large integer multiplication base 2 to the 34 base 264 or some such. The standard long multiplication in binary is pretty simple. The issue is probably that binary is not space efficient. I don't know. Yeah, I don't know either. I just know that this is implemented in some libraries. So like it is used. The question is where it's used and stuff like that we have to figure out. So let's read in this vector that they have in the example. It's going to be 32, right, 32, 52, 61, 60, 34, 16, and 5, and then 0. And this gives us back 2, 5, 6, 6, 0, 0, 7. Okay, I'm actually really happy that that seemed to have worked. So now we have our... this is definitely inefficient. There's no doubt this is inefficient. But works. Okay, so there's probably a better way to do this. So we're gonna say, do the carrying operation. Perfect. Operations. Okay, so we've got split and zero pad. We've got our carry operation. So now it looks like the only thing we have left to do is the FFT bit. So let's just wrap it all together into the Schonhage Strassen bit. In fact, let's just start doing it, okay? We're going to do it in the REPL over here first. So we're going to say split and zero pad of 1, 2, 3, 4, and then 5, 6, 7, 8. And we're going to call those vectors A and B is going to be equal to that. So now A is this, and B is this. So if we do FFT of A, what do we get? We get a complex array, which is already not great. And it's going to be 10. It's not really anywhere close to what they're showing in the example. So we get 10, some weird imaginary number. So they have 10, 329, 298, 126, 2, 271, 43, 301. We're getting 10, something like 5, something like 2, something like 3. Okay, and I think this is specifically because the FFTs are not in... Okay, what if we just go for it? What if we try it and see what we get out, okay? So we just do the FFT forward, FFT back. We know it's a convolution. That should do a convolution, right? So we'll give it a go and see what this does. So we're going to say fa is f of a is going to be equal to FFT of a. FB is going to be equal to FFT of b. Now we're going to say FBA, not FBI, is going to be equal to FA dot times FB, right? Okay. Now we're going to do IFFT of FBA, and this gives us 32, 52, 61, 60, 34, 16, 5. Hey, all we have to do is round these guys. So if we, can we do ceiling? I mean, they're so close to what we want them to be. So let's just say we want to round these and see what happens. So if we round int here, round doesn't exist. I think it's this one. Let's just do ceiling, I guess. Sure. No mathematics. Oh, I probably need round dot. That's what I needed. I gotcha. No math matching round, type int64, complex. Do we have to do the real? Round dot of real dot this? Oh, that? No. Okay, let's just say we had FBA, so we're going to say BA is going to be equal to IFFT of FBA. Again, the names aren't perfect, but we'll get there. IFFT of this. It's so close, we just have to round that. So we have BA, so let's do real of BA, right? So let's do round dot of real of BA. And let's change that to an integer. Come on, this is super close. All right, so now we're just gonna do Schonhage Strassen down here. Function Schonhage Strassen. I'm actually amazed that this is kind of working. So we're gonna take in two vectors, A and B, or two numbers, A and B. And here, first thing we're gonna do is, I guess we're gonna call it VA and VB. Again, bad names, we'll fix the names later. Is gonna be equal to split and zero pad of A and B. The next thing we're going to do is we're going to say we need to FFT forward and FFT back. I think we can do this all in one fell swoop. So we're going to say, I guess we're just going to call it V final is going to be equal to FFT of VA. dot times FFT of VB. Then we want to do the IFFT of these guys. And then we want to do the real of that. And then we want to round that to the nearest integer. Int. Okay. And then in here we're going to do carry of VF. And then finally we want to return vector to int of VF. Does it work? All right, let's see what happens. Schonhage Strassen of 1, 2, 3, 4, 5, 6, 7, 8. We get the right number. So let's just try some random numbers and see what we get here. So we're gonna do. Let's do. It doesn't really matter. 1, 2, 3, 4, 5, 6, 7, 8, 9 with 9, 8, 7, 6, 5, 4, 3, 2, 1. This is gonna give us that number. And so let's do ants minus. And then we just do the multiplication ourselves. 1, 2, 3, 4, 5, 6, 7, 8, 9 times this. And let's just do a multiplication in here. Got it working. Okay, that I'm that was it. This is the whole algorithm. Like, that's it. I don't know what to say about that. It's remarkably simple. The only trick is that you have to see that... Wow, what? I don't know. Guys, we got a whole algorithm implemented in, what was that, 30 minutes? We haven't even been streaming an hour. We started literally 20 minutes into stream. It's only an hour into stream right now. Like, that was the quickest implementation we've gotten. Obviously, there's still a lot left to do. We have to figure out how to do the integer-based FFT and stuff like that. Performance is likely to be great with 10K plus digits. We could try 10,000 digits. No, let's not do that. Okay, so let's go ahead and add this implementation. Git add Schonhage Strassen, git commit -m, adding a simple skeleton for Schonhage Strassen algorithm. Git push, origin master. That's it. Algorithm speedrun. Okay. Yeah. Okay. Let me get some water. And let's yeah, the method worked. Literally, all we had to do was split and zero pad, round our FFT forward, or round the convolution, carry it, and then return vector to int. Everything worked. So this is like a first in Simuleo's history that everything seems to have worked first time, and I'm kind of baffled because I was fully expecting to break at this FFT part right here. That's where I was expecting it to break. Because I thought maybe the FFT needed to be in the integer domain specifically, but I guess a convolution is a convolution, and I guess it's fine. Cool. Okay, so let's talk about what's next. I'm just taking a minute to soak it in that we literally got an implementation done in 30 minutes for an algorithm that I've been trying to figure out for the past 2 years. You know, like ever since I heard of this algorithm, I'm like, that is the dumbest thing I've ever heard. It's amazing. And here we have implemented it in 30 minutes. So convolution is a convolution. You just get some floating point rounding noise with large FFTs. The next possible thing to do is doing the FFT yourself, basically. Right, so that's the question. So the question next I have is, what is the difference between a number theoretic transform and an FFT that we did with FFTW? And what was this? A clock, modular arithmetic. Oh, sure. Okay, so this is the next thing I want to kind of talk about, because I've got a feeling going full hog with FFTW is probably a bit much. We probably could get away with just doing integer arithmetic. I'm just still blown away. We're done. Okay, so obviously this all relies on a good intuition for what a convolution is, which admittedly I don't have, and I know we're gonna have to go into. So this upcoming week, we're gonna kind of go into the convolutional theorem and try to explain how it works from a fundamental perspective. That's my goal for next week. By the end of this year, I want 3 things to be done. 1, I want to have revised the FFT chapter in the algorithm archive. 2, explain the convolutions and the convolutional theorem. And 3, get the Schonhage Strassen algorithm implemented in the algorithm archive and on video. That's where I'm at. How does the FP rounding noise in the FFT scale with the size of the input? That I'm not sure. We could try larger inputs, but I think we're not gonna. Okay, how about we do that? Okay, let's just try it out right now. We're just gonna do something dumb, and we're gonna see where we break. So let me do. I'm gonna create a large vector of integers. So can I do rand? Let me try this. Rand of int 10. What does this do? Rand of int. Okay. And let's just do modulo 10. There we go. Mine is 5. What? I think I'm dumb. How do I get... How am I getting negatives? Oh, because some of these are negatives. Okay, fine, fair enough. So we specifically want positives. So what happens if I do... What does rand of int even do? 10? No method matching rem... Huh? Okay. Oh, it creates a 10 element array. Okay, let's just do rand of int modulo 10. And let's make sure it's positive by doing absolute value of that. Okay, so that'll be that. And then we want to populate an entire array with this. So I think, can we do a dot modulo? Is that something we can do? But O-squared and recurrences are popular. Basically, the main source of the error tends to be trigonometric recurrences for fast sines and cosines. Dylan Beetle, BD, sorry about that. Thank you so much for the raid. How are you? How was your stream? I hope it all went okay. Yeah, so what do we have here? Newt Zero, thank you so much for following. Really appreciate it. I.e. multiplying 2 giant numbers, do you expect rounding in each digit to be roughly integer? Basically, the main source of error tends to be trigonometric function. Okay, I've now separated the creation of edgework objects from their initialization, hopefully without changing behavior. Now to test. Also fun, advent of code, day 13. Oh, sounds cool. Yeah, sounds cool. How's it going? It's going okay. So for those of you guys who might have just jumped in, we're doing literally what the stream title says, which is trying to figure out how to multiply 2 numbers. Now, I know what you guys are thinking. Like, who doesn't know how to multiply 2 numbers? I learned. I don't. And I need to learn. So that's what we're doing. And so the easiest way I could see to multiply 2 numbers was with the Fourier transform. There's probably an easier way to do it. I just don't know it. And that's kind of where we're at. So the idea here is that you can do a multiplication via a convolution, via the convolutional theorem. So the idea here is that you have 2 strings of integers. By convolving one string with the other string, that is to say, finding some sort of, in a sense, similarity matrix between the 2 of them, you can then create a new array, and by carrying that new array, basically doing the operation where you send anything above the tens digit to the next digit. I'm doing a bad job of describing this. You can do multiplication. That's what we have. I'm sorry. So test pass, cool. You want to vectorize the abs too? Oh, correct. Thank you for that. Abs dot. Oh, that's exactly what I want. Perfect. Okay, so let's do 100. And we're going to set this as A is going to be equal to that. And we're going to say B is, A is going to be equal to this, and B is going to be equal to that. Okay, so this is going to be our set of... Perfect. Okay, so now what I want to do is vector to int of A, perfect, times vector to int of B, and we're going to call this the solution, is equal to that. We're in the negatives. So we're we're above the cap there. Okay, so let me right. So let's just do Schonhage Strassen on what we have here. So it's gonna be vector to int of a vector to int of b. Great. Okay, we got the same number at least. So solution minus. Perfect. Oh, I can't believe it. It's fine. It's fine. It's fine. Okay. What do we have here? Full two strings is faster for smaller integers and easier to understand than Schonhage Strassen, though. Right, yeah, it probably is. Hi, Dylan and Raiders. Basically, I'm developing command line app for video games. Let's see. Kurtsuba is pretty much the only thing that's faster than long multiplication for numbers most of us ever need. Right. Kurtsuba is what most big int libraries use, I believe. Just wait until he discovers Fur's algorithm. Isn't Fur from Matrix? I've been doing the advent of code with Haskell to learn Haskell better, and my brain is melting. GPM uses long multiplication for small numbers, and then Kurtsuba for larger. Then a few versions of Tomb as the number gets larger, and then SS when they are sufficiently ridiculous. Right. There is actually stuff beyond Schonhage Strassen for even more ridiculous integers. But yeah, for the most part, you guys are right. Schonhage Strassen is not used for the bulk of cases. But what's interesting about Schonhage Strassen is the fact that you use an FFT to do the method. That's the thing that I find interesting. I know long multiplication is a convolution, right? Like when you look at it, you see that, but you don't. I didn't think of that. Like when I did multiplication, I never thought about thinking of it as a convolution. And this is something that like helped me understand kind of, it helped me understand multiplication. I thought it was pretty cool when I saw it. So I don't know, I'm happy with that. Let me see, what do we have here? So the next thing I kind of want to look at is figuring out the number theoretic transform and stuff like that. Maybe later. Okay, faster integer multiplication, the Fur algorithm, I probably can't pronounce it. For more than 35 years, the fastest known method for integer multiplication has been the Schonhage-Strassen algorithm. Runtime, oh right, this one's, okay, so this is the one that people know about but is not actually implemented in practice. First is better than SS when the numbers need half the mass of the universe to represent. Yeah, that's kind of what I understand. I think multiplication can be done in n log n for huge integers. I think, is that not what this one does? Oh, it's n log n log n. How? N log n is the... Stop it. N log n is the complexity of the Fourier transform. Right? So where does the log n come from? That's the hypothesis, but even for is not n log n. Interesting. See, this is the thing. So I've been wanting to do a series. FFT is considered n log n if you treat the elementary operations as O1. Wait, what elementary operations are you talking about here? Sorry about that. The elementary operations of what? Can I link? Yeah, please do. Okay, so I really do want to do this series where we go through like very simple operations, multiplication, maybe matrix multiplication, and we kind of explain what the hard part is. Like for example, FFTs, everyone knows and loves FFTs, but what most people don't know is that for higher dimensional FFTs, the slow part is not the operation. The slow part is the transpose for the operation, right? Let's see what we have here. And there's a bunch of little things like this that you just don't think about. And I'm not looking for something that's like, you know, oh, how complicated can we make matrix multiplication? That's not what I'm asking. I'm asking, are there ways in which multiplying large matrices help us understand multiplication as an object? That's kind of what I'm thinking about. Do we have any multiplication algorithm for that? For what? Do we have fast multiplication algorithm for numbers so large that it can't fit them in memory all at once? Yes, so that was a good question. I think, oh, who was it? Was it, oh, he's in our community. I can't remember what he goes by. But yeah, one of the people in our community definitely looked at that. And they were talking about it, and it was super cool, and we never really got anywhere. I think it was discovered recently, like in the past year. It's not practical at all. New York? Could have been New York. I mean, maybe it was just Ben. Maybe it was Ben. He did some stuff a while ago for it. No, maybe it wasn't Ben. I don't remember. He did some sort of representation for large integers. I know Ben did that, but I don't think that he did the question of how do you do multiplication for integers that are like bigger than you can fit in memory. Ben was doing big integer stuff a while ago, right? So there's this thing, you can do naive convolutions by treating blocks of FFTs as your digits. You can do naive convolutions by treating blocks of FFTs as your digits. Interesting. I remember talking to him about it, submitted on the 20th of November 2020. Well, if it's true, and yeah, it's super cool. Yeah, it's amazing if true. Let me read the abstract here. We present an algorithm. Let me make this a bit bigger. We present an algorithm that computes the product of two n-bit integers n log n in O n log n bit operations, thus confirming the conjecture of Schonhage and Strassen from 1971. Our complexity analysis takes place in the multi-tape Turing machine model, with integers encoded in the usual binary representation. Central to the new algorithm is a novel Gaussian resampling technique that enables us to reduce the integer multiplication problem to a collection of multidimensional discrete Fourier transforms over the complex numbers whose dimensions are all powers of 2. These transforms may be evaluated rapidly by the means of Nussbaumer's fast polynomial transforms. Okay, so basically they're saying that multiplication isn't just a convolution, it's actually literally just the DFT? Is that what they're saying? So if your numbers don't fit in memory, you could FFT numbers that do fit in memory. Oh, right, that's pretty cool. Yeah, that's a good idea. E.g. convolution reverbs use a concept known as frequency domain delay lines for efficient long convolutions using FFT blocks of much shorter, because overall it ends up being more efficient and you need less latency. I'm just kind of curious if you could use such a partial multiplication algorithm to produce partial results for absurd Googleological equations. See, yeah, I mean, this is a good question, and I wish I had an answer for you guys, you know? Also, can I just say, like, I don't mean to brag, but I think we have, like, the most intelligent Twitch chat on the platform. Like, I'm just, you guys are amazing. Like, I don't know what else to say. It's just that, like, you guys are, like, blowing my mind with this stuff, and I have a PhD in computational physics, and I work at MIT. You know, like, it's pretty amazing, and I don't know what you guys did to get so smart, but whatever you did, keep it up. Let me get some water. Okay, so let's think about this. Yes, smart. The next thing I wanted to talk about, though, was actually the number theoretic transform. I only come here to get my ego massaged. That's fair. I'm over here, like, that's the thing, though. It's so crazy because I'm sitting here and I'm like, oh, let me try to understand the number theoretic transform. And you guys are like, oh, we can do matrix multiplication, or we can do multiplication with, I don't know. I wish I was that smart. I'm not. Okay. I'm going to read this section on the number theoretic transform. And then what I might do, guys, is I do have some guests over, and I've got to do some video editing. So I might have a short stream today. I said I was gonna have a short stream. We're gonna do a short stream. We'll come back tomorrow and we'll do our regular 2-hour stream and stuff like that. But thanks, man. I'm just an MSc student though. Wait, that means I'm not that dumb. I said the word Googleological. That I just made up. That means I'm smart. Yeah, I can tell you all about floating point FFTs, but sadly no practical experience with number theoretical ones. Number theoretical transforms are kind of outside DSP fields, data signal processing fields. Right. I instinctively washed off a piece of toast in the sink today. I'm not that smart. Okay, so let me read this section on number theoretic transforms, and I think maybe we'll kind of think about how we're going to implement this, and then we'll call it for today, and we'll come back tomorrow and we'll keep looking at this. I essentially just want to plan forward. Again, I told you guys what I want to do by the end of the year, and now there's good reasons I want to do this, like really good reasons I want to do this, because how do I put this? The fractal flame method that we were working on before, the flamify package, we're going to do that. It's going to keep going, but it's going to keep going in January. I want to take a step back and implement the convolutions first. I want a good base to work off of, so that if people have any questions about any part of the fractal flame method, they can do that. And so having a method that is so fundamentally reliant on convolutions and is also quite cool, I think is something that I really want to do before doing the fractal flame method. And so let's do it in the right order. Crazy algorithms and then crazy applications to algorithms and stuff like that. Okay, Rip Toast, it's a bunch of soggy crumbs in my mom's sink. You didn't wash it down? Okay, so number theoretic transform. The number theoretic transform is obtained by specializing the discrete Fourier transform to ZP, the integers modulo prime P. Right, this is a finite field, and the primitive nth roots of unity exist whenever n divides P minus 1. So we have P is equal to xi n plus 1 for a positive integer xi. Specifically, let omega be a primitive P minus 1th root of unity, and an nth root of unity alpha can be found by letting alpha is equal to omega xi. I really wish I could speak Greek. I mean, I've read Greek before, but xi is hard to pronounce, and I don't know if I'm even pronouncing it right. I used to pronounce it z, but I don't know. Okay, so e.g. for P is equal to 5, what is P? P minus 1 is going to be your... it's going to be what you're moduloing over. So prime P. So P is 5 and alpha is equal to 2. So what is alpha in this case? Alpha is the nth root of unity. Alpha can be found by letting alpha is equal to omega. Okay, omega, see, so omega, is this your twiddle factor? So e.g. P is equal to 5, alpha is equal to 2. So it's going to be 2 raised to the 1, it's going to be 2, 2 to 2. So why is alpha, okay, so alpha is your root of unity. Okay, I think I'm understanding the way this works. I need to kind of think about how we're gonna describe this. So essentially you're working on a clock. You're working on a clock with n digits in it. So it could be 12, that's your normal clock, could be 10. In particular though, we want a clock with a prime number of elements. So this is gonna be 2, 5, 3, 7, all these different primes, 13, they're all primes. And then what we're going to do is we have some sort of base, which is going to be your root of unity that you're working off of. And so this is to say you have 2 to the first, 2 to the second, 2 to the third. Now, does alpha also need to be a prime? I'm not really sure. Probably. And so the idea here is that you fill up your DFT operation. This is the DFT operator in here with integer values instead of filling them up with complex values. And then you essentially do the multiplication like you normally would. So essentially this is creating a new DFT matrix to operate over. Now my question is, how do you do this coolly tuki? The number of theoretic transforms may be meaningful in the ring Z over M, even when the modulus M is not prime, provided a principal root of unity, root of order N exists. Special cases of the number theoretic transforms, such as the Fermat number transform used by the Schonhage Strassen algorithm or the Mercy number transform, is use composite modules. So x squared plus 1 is equal to 0. Mod 5 has 2 and 3 as roots. So 2 and 3 are like roots of unity in modulo 5. No, x raised to n minus 1. I'm taking the cyclomatic polynomial, so ignore x minus 1, x plus 1 terms. I'm a bit lost with that statement. I'm sorry about that. Okay. Yeah, in Z5, it works. So basically, where in FFT, you rotate complex numbers around the origin. Here, you rotate along mod P. Right, that's exactly what we're doing. Like, that's my intuition. The question is, how do we do an efficient implementation of this? And do we need it to be efficient? Or can we just say, I think we're going to have to implement our own FFT to do this the right way. The problem is, if you implement your own FFT, it's going to be slow. Right? I mean, you've got the recursive method and the bit reverse ordering method. The bit reverse is faster than the recursive method. Let's just play with it. Okay, so here are things that I'm thinking about right now. And I'm not really sure the best way forward. Huh? Really? Okay, that's fine. For some reason, my eraser is not working on my pen anymore. Must have been an update and it just kind of broke it. Okay, so let's talk. The Schonhage Strassen algorithm, right? So we have our basic implementation. The next steps are going to be 1, understanding the convolutional theorem, right? We've done a whole bunch of streams about this, and we're kind of there already, convolutional theorem. Okay. The next thing we have to understand is the number theoretic transform. Again, we have an idea of how it works. It's literally just the same thing as doing your FFT along the circle, the complex circle. It's just now it's along an integer domain with some sort of modulo arithmetic. Fine, fair enough. And once we get these two, honestly, we're at the stage where the Schonhage-Strassen algorithm is relatively straightforward. But the question becomes, how do we do Cooley-Tukey? Cooley-Tukey? On integer space. So we'll say integer on ints. So that's kind of where I'm at here. We can do Cooley-Tukey on ints. It's not hard. We can do that method. But I guess the question is, how do we make it efficient? Efficiency? Question mark. And I guess the answer to that is we probably don't need it to be efficient, right? Like what we're doing here is just kind of implementing the algorithm, making sure it works. And that's fine. We already showed it works. So now we just want to make it so it's more perfectly, like more representative of the algorithm that people want. Okay, so this is where we have for the Schonhage-Strassen algorithm. Before ending, again, it's going to be a short stream. I've been streaming for 1 hour, 30 minutes. Sorry, you know, like, I'm not even speaking English right now. It's going to be a short stream. We're almost done. There is one other thing I wanted to talk about, which is kind of the direction of the channel. Again, I always talk about the direction of the channel. Everyone knows. I try to make sure that I wrap it all up and everyone understands where we're going. So, okay, I will be quitting my MIT job in a few days. So at the end of the year, rather as of January 6th, 2020, I will no longer be working at MIT. I have a new job that's coming up that will allow for me to work on my online content on a much, focus on my online content a lot more. And so in the upcoming year, I've got a whole bunch of really big projects that I really want to do that are really going to, I think, like, it's going to be awesome. Like, I'm really excited for it. And so the big projects that we're currently working on that everyone knows about are F-Flamify, which is basically the act of turning any image into a set of fractal flames. Then the other one that we have is Quiltify. It's not as big, but I like it just the same. Right. And then we've got all of these other, like, really big, how do you say, like, these ideas that I want to work on, that I just haven't had time to work on. I've got one that's a knot theory example, knot theory, which is the question of how do you turn any knot into the idealized form of that knot? And that's a very good question because it's really hard to do. Except that I had found a way to do it during my PhD. If you embed a knot into a superfluid and treat it as a superfluid vortex, and then you change the PDE to be a slightly different PDE from the Schrodinger equation, you can actually make it so the vortex will move and not reconnect. And in the act of not reconnecting, it will also shrink to the optimal knot form. And so what we could do is we could create a very simple method that embeds a knot into a superfluid, and then essentially, like, create the smallest form of the knot. Can you do it in 4 dimensions? That's kind of part of the question I have. Because, okay, hear me out. I've been trying to think of a reason why you'd want to do a 4-dimensional superfluid. And I couldn't think of one, except for the fact that knots are parameterized in 4D space. So that's kind of cool. So anyway, so this is one that I really want to try. And it's like a new research project. So this is a new research project. There's a paper that could come out. This is another one, paper could come out. There's a whole bunch of, like, really cool things that I want to do. There's one more that's really cool and a paper could come out of it. Which is the, obviously, I know I did this a long time ago, but the transpose. Look, I realize this isn't going to be the best video ever, but it could still be a research paper that I could get out in the next year. And so what I'm looking for are these projects that are actually, like, research related projects, things that you could actually, publish, right? But also things that are cool and visually appealing and things that, you know, people would want to watch, you know? And I think I've got a bunch of these. And so I just want to knock them out. And that's the plan for next year. I just want to just put my head down and just start working on these projects that are like independent research projects, that are like super just visually appealing and interesting. And I can guarantee you that next year is going to be very interesting for content creation. I'm going to do my best to ramp up everything that I'm going to do my best to like turn my channel into something amazing. And we're just going to see how it goes. If I can ramp it up well, if I can't ramp it up well, next year is going to be the year that we figure that out. So yeah, there's going to be more streams, a lot more streams. I'm planning, the reason I couldn't do streams before is because I just couldn't do it with my Klima job. But now that I'm no longer working for Klima, I've got plenty of time. So I should be able to do like much longer streams than I used to do. And they'll be much more interesting as well. Like akin to the Flamify streams where they're just like kind of weird applications that like people wouldn't normally think of. Like I had this idea of starting a lot of my videos with the phrase, you know, here's something you've never seen before. And I want to like, I want it to be something that no one's seen before and something that no one's thought about before. And I really want to do that. I'm pretty excited for it. So anyway, I just wanted to say that, you know, I took a week off. I'm happy I did take a week off. Again, a lot happened last week. My girlfriend got her PhD. I ended up leaving the MIT job, all this kind of stuff. So it was a good week to take off, but I'll be back starting next week. Again, doing, you know, short streams next week, but then the week after that, I'm hoping to ramp it up and start doing longer streams and just really start knocking this stuff out. And that's kind of the plan. What do we have here? There are no knots in 4 dimensions. Perhaps, but I was still trying to make a joke. Oh. That's fair. Okay, so that's where I'm at. I just wanted to let everyone know that's the plan. And I think that will be it for today, guys. So let's see who we want to raid at the end of stream. We've got Lana who's live. Let's see, Rocket Sage. Let's do Lana, actually. Let's raid Lana. Let's go start the raid on Lana Lux. And that will be it for now. We'll be back tomorrow. I'm actually really excited. Like, I don't know how to properly express how excited I am. Like, when I got the new job, I was kind of excited. I was like, yeah, okay, this will be good. But I think I was just so jaded from working in academia for the past 6-7 years, maybe even longer if you count some of my undergraduate time when I was essentially a graduate student, that I didn't really think like getting a new job would be this exciting. But this new job is actually really cool. Like you'll hear about it in January. I'm not going to tell you guys what it is until then. But when you see what it is, you're going to be like, yeah, that was the perfect job. And you're going to be pretty excited for it. Or I hope so. I mean, there's a lot coming up. That's all I want to say. Anyway, that's it for now. Let's go start the raid on Lana. Thanks for the stream. I'll try to catch tomorrow's stream. Thanks for the stream. Yep, so starting tomorrow, I'll be streaming again at the normal time, 6 o'clock p.m. Eastern. I'll just be doing a 2-hour stream like normal. But again, the week after that, we're going to start ramping up and doing longer streams and stuff. Looking forward to hearing about the new job. Again, can't tell you guys until January. It's not that there's like an NDA or anything like that, but you know, I'm excited for it, but we haven't signed any paperwork, so you got to make sure it actually, you know, works out. Okay, that's it. Thanks, guys. Let's go start the raid on Lana Lux. And that is it for now. So thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos. Tomorrow, 6 o'clock p.m. Eastern. Got a lot of stuff to do. Pretty excited for it, and I will see you then. Bye, guys.